it. Molecular geometry is a three-dimensional structure or arrangement of atoms in a molecule, which helps to determine the polarity, reactivity, phase of matter, and many more properties of molecules.
Wow, so it's quite an important topic then.
You don't say.
So how do we determine the molecular geometry of molecules?
For that, we must be acquainted with the dot and cross diagrams.
But we've already learned about the dot and cross diagram in your previous lessons.
Yeah, but remember that the dot and cross diagram does not determine the shapes of molecules. Rather, it's the first step in predicting shapes of molecules.
I see.
Likewise, it helps us identify the bond pairs and the lone pairs present in the molecules. Do you recall studying about them?
Yes. Bond pairs are the pairs of electrons involved in the bonding, while the lone pairs are those which are not involved in bonding.
That's right. You must also remember that the shape of a molecule is dictated by the number of electron pairs around the central atom of a molecule and the nature of these electron pairs, whether they are bond pairs or lone pairs.
So, how are these electron pairs responsible for the shape of the molecules?
Well, since electrons are negatively charged, an electron pair in the bonds surrounding the central atom in a molecule will repel other electron pairs.
Oh.
This repulsion forces the electron pairs to move apart as far as possible within the borders of the bonds between the atoms in the molecules. Moreover, this concept of electron pair repulsion theory is known as valence shell electron pair repulsion theory, or simply the VSEPR theory.
Oh my god, that's quite the mouthful.
Yup, that's why we simplify it and pronounce it as the VSEPR theory for ease of use.
VSEPR theory. That sounds much better.
The main idea of the VSEPR theory is that the atoms in the molecules will always tend to arrange themselves in a way that electron pair repulsion is minimalized. This arrangement of the atom, in turn, determines the three-dimensional shape of the molecules. Also, note that this theory is quite crucial while determining the molecular geometry of the molecules and ions.
Got it.
Now, let us use this theory to determine the shapes of molecules which only have bond pairs of electrons and no lone pairs.
Alright.
Let's consider a simple molecule of beryllium fluoride, or BeF2, and start with its dot and cross diagram.
Oh, can I hop in and give it a shot?
Sure, why not?
So the dot and cross diagram of BeF2 would look like this. As we can see, the central beryllium atom has two bond pairs of electrons.
Correct. So, as per the VSEPR theory, these two bond pairs of electrons sit at an angle of 180 degrees with minimum repulsion. Hence, the molecule is linear.
Cool.
Similarly, just like beryllium fluoride, beryllium hydride, or BeH2, also has a linear geometry.
Oh, so are there other molecules too which have a linear geometry?
Of course, carbon dioxide also has a linear molecular geometry.
Really? But as I recall, carbon dioxide has two carbon to oxygen double bonds. So wouldn't that affect its geometry?
Well, only the sigma electron pairs are responsible for the molecular geometry, not the pi electron pairs. So, the multiple bonds are best considered in the same way as single electron pairs.
Finding this helpful? We have additional learning resources to offer. For Cambridge IGCSE and AS A-level subjects.
Got it. So the 4 electrons in each double bond repel other electrons in a similar way as the 2 electrons in a single bond?
Correct. That's why the bond angle is 180 degrees in carbon dioxide as well.
Understood.
Likewise, the ethyne molecule also has a linear geometry with all of its 4 atoms lying in a straight line.
But what about polyatomic ions? Are there any ions having a linear geometry?
Well, anions like the azide and thiocyanate ions and cations like the nitronium ion also have a linear geometry.
Oh. I get how molecules with a linear geometry work now.
Great. Moving on, let's discuss the geometry of boron trifluoride.
Oh, wait a second. I know that just like beryllium fluoride, boron trifluoride too is an electron deficient molecule. That's because its central atom, boron, has only 6 electrons in its outer shell.
That's right. These 6 electrons form 3 bond pairs which repel each other equally, thus forming a trigonal planar molecule with bond angles of 120 degrees.
A trigonal planar structure?
Yep. Note that it's quite difficult to represent the three-dimensional molecule on a paper. So, there's a simple convention when drawing a 3D shape. We use a normal line to show a bond in the plane, a dotted wedge to show a bond going into the plane away from you, while a bold wedge is used to show a bond coming out of the plane towards you.
Interesting. So let me guess. Boron hydride, or BH3, also has a trigonal planar structure, just like boron trifluoride.
Bingo, good guess. Apart from that, organic molecules like ethene also have a trigonal planar structure.
So each bond angle in the ethene would be 120 degrees, right?
Well, not exactly. In the case of ethene, the HCH bond is slightly less than 120 degrees, while the angle of HCC bond is slightly greater than 120 degrees.
Really? How so?
The bond angles in the ethene molecule are not exactly equivalent, as each carbon atom is bonded to 2 different atoms, hydrogen and carbon. For bond angles of exactly 120 degrees, the atom must bond to the same atom.
I see. It means the bond angle would be approximately 120 degrees, but not exactly 120 degrees.
Correct. To add on, some ions like the carbonate, nitrate and methyllium ions also have a trigonal planar shape.
Oh, do these ions also have a bond angle of about 120 degrees?
Indeed. Now let's take a look at the molecule having 4 bond pairs. You do know some examples, right?
Of course. Methane has 4 bond pairs.
Correct. Methane has 4 bond pairs of electrons surrounding the central carbon atom, and they repel each other towards the corners of a regular tetrahedron. Hence, methane has a tetrahedral structure with all HCH bond angles equal to 109.5 degrees.
Got it. So what other examples are there?
Well, if we replace all hydrogens of methane with chlorine, then we'll get carbon tetrachloride, which too has a tetrahedral structure.
Cool.
To add to that, the sulfate ion is another example, where all the oxygen atoms are arranged at the corners of the tetrahedron surrounding the central sulfur atom. Likewise, sodium borohydride is a salt, which consists of a tetrahedral borohydride anion.
Cool. So teacher, are there other types of molecular shapes as well?
Yes, of course. Next up is the octahedral structure.
What does it look like?
You should have seen it before. Are you familiar with sulfur hexafluoride?
Yeah. Sulfur hexafluoride has a central sulfur atom that has an expanded octet state with 6 bond pairs.
Correct. The 6 bond pairs of electrons around the central sulfur atom push each other as far as possible. This means 4 fluorine atoms are arranged in a square around the sulfur atom, and the remaining 2 fluorine atoms are positioned above and below the square.
Wow.
If lines are drawn from each fluorine atom to its nearest neighbors, the result is an octahedron with 8 sides. Here, all FSF bond angles are 90 degrees.
I see. But the structure looks quite complex and difficult to imagine.
That's understandable. Since it's a 3-dimensional structure, it's quite challenging to show it on a 2D board.
Register now for free.